Now in exercise 5C, we'll be seeing the application of integration. So we know that integration, mathematically, is the reverse process of differentiation, and we've just established nicely that if we start off with a displacement function, so I've got x as a function in time. If I differentiate that, so I denote that with that, which is f dash t, then I get velocity. And so if we then take our velocity function and differentiate that again with respect to time, always with respect to time, then we get acceleration. So what you would know is that the reverse is integrating. And if I'm given an acceleration function, then if I integrate it with respect to time, then it would take me back to a velocity function. So I've stated that here. Since the inverse process of differentiation is integration, it stands to reason that the integral of an acceleration function, so it must be the acceleration function that you're integrating if you want to get velocity. And don't forget your c. Now that is really, really important because you'll see that there are times when c ends up being 0, but you'll also see there are situations where it's really important that you've established if there is a constant belonging to, in this case here, say the velocity function, because what you will then do in a lot of cases, you will go on and you will integrate your velocity function, which would take you back to the displacement function. Now, if your velocity function isn't complete with the c, then you're also going to miss some terms in your displacement function. And then again, even when you integrate your velocity function and you get back to your displacement, you will also have c again. Another way of thinking about it is you could think about the area under the curve. The area under the acceleration time curve, and I need you to correct this, that's not value, that is actually velocity. You probably picked that up. So could I get you to fix that up in your notes? The area under the acceleration curve, because that is what integration does, gives us the area under a curve, would give you the velocity. So obviously it's a definite integral. We will have definite starting point, definite finishing point, which would enable us to visualize graphically the area under the curve from a starting point to a finishing point. So just in summary here, you can see displacement, the aspects of motion are displacement, velocity and acceleration. So there are three measures. Displacement, we use the notation x. We know that x is a function in time. The calculus for obtaining x would be, we would want the integral of velocity. So if we were wanting to find displacement, we would need to know about velocity. And that's probably the situations you're going to see in this exercise, because this exercise is going to focus on integration. The previous exercise, you were most commonly given your function in time for displacement because you went ahead then and differentiated. So it's more like exercise 5B was about this column, moving from displacement through to velocity by differentiating, and then through to acceleration by differentiating again. Whereas now in 5C, you're probably going to be given a statement about acceleration, which will enable you to start here. You'll know acceleration, and you'll be moving back to velocity and then back to displacement. In order for you to be able to do that, you'll have to interpret some words, and I've already spoken about the importance of the words. The words in the question are, in many cases, your only assistance. So things like initial means at the beginning. Now, what does that tell us? It doesn't really tell us anything about velocity or acceleration at the beginning. We'd need to be told that. The only conclusion we can make from initially is that t is equal to 0. T is equal to 0 is the only assumption you can make. You might be told, as part of the question, that velocity is also equal to 0, that the particle was at rest at the beginning, or was at rest initially, but initially on its own just means time is 0. The next point, a particle is at rest. Now, if you're told the particle is at rest, then velocity is 0. So these two things may coincide. It may say initially the particle is at rest. What conclusion do you make from those words, that sentence? Initially, you'll be writing when t equals 0, particle is at rest. You'll be interpreting that as v equals 0. Now, you can see that these are really going to be important when you're integrating, and especially when you're trying to find your constant. So this constant back here, or the constant in your displacement function, because to be able to substitute t equal to 0 into a function is simplifies it very quickly and enables you to find the values of c. I think, I talked to you the other day about maximum and minimum displacement, and you seem to have a very good understanding of that. The maximum or minimum displacement occurs when, so we think more about our graph here. So if I've got a graph of displacement, where does it ever get to a max or a min, or a max or a min, is where we would previously have just said, well, the first derivative is equal to 0, or the gradient of the tangent is equal to 0. Now, once we've got an application of our variable, and in this case it's displacement, we can give another name to our first derivative, and in this case it's going to be velocity. So we'll know that we've got maximum or minimum displacement when our actual velocity is equal to 0. Why? Because, like I've just said, the velocity is the expression or the application of the first derivative of displacement. With a maximum or minimum displacement would be found by, what would we need to do? We would need to solve v is equal to 0, and then when we had our value, our velocity function would be in terms of t. Velocity, remember, is all of our functions are going to, our variable is going to be t. So we'll solve v equals 0, which will give us some value of t, or maybe 2 or maybe 3 values of t. We then substitute this or these values of t back into the displacement equation to be able to determine the displacement. So take the questions slowly, take the concepts slowly, think about exactly what you're being asked to do. And like always, you know that from one question to the next, you might be doing different things. You'll be given different information. And it's more, because the maths won't be any different or new, there's no new maths. It's what you've really got to focus on in this exercise, and probably in this whole chapter, is what is the actual application of that mathematical process? So what are you doing here with respect to motion, which is time, displacement, velocity, acceleration? What are you doing when you solve something equal to naught? What is it telling you in reality in terms of time? Are you finding out something about time? Or are you finding out something about the velocity? Or are you finding out something about the displacement? What is it that you're actually finding out when you perform a mathematical operation? And these are mathematical operations. Putting v equal to naught is a mathematical operation. Subbing t equal to naught is a mathematical operation. Now, if you're struggling with that, they're the questions I would like you to ask me or a student next to you. And if the student can't answer it, then please make sure you ask me, because I believe your success in this chapter depends on your understanding of what the mathematical process is calculating for you in terms of real things like time, displacement, velocity and acceleration. So that's really what our focus has to be. That's the understanding that we're building. It's not about, you've already perfected differentiating and integrating. It's now its application. I've paused the video and filled out the rest of these because I'm running out of time on the video, but in a similar way to the concept of velocity being the derivative of displacement, then acceleration is the derivative of velocity. And if we wanted maximum minimum velocity, then we're then talking about acceleration, because again, if our graph, if rather than displacement, this was velocity, then it was reaching maximums and minimums when the first derivative of velocity is equal to naught. And the first derivative of velocity is called acceleration. So we would be setting up an equation as our statement if we were finding maximum minimum velocity. The other concepts you come across are constant velocity. So that is just what I think your basic understanding of those two words would be. If it's a constant, then velocity is not going to vary. Our variable is always time. That means our equation for velocity doesn't have a t variable in it. It is only a number. So if our velocity function doesn't have any t, then when we took the first derivative of displacement, we arrived with no t. We arrived just with a constant. And similarly for constant acceleration means the second derivative of displacement would be a constant, or the first derivative of velocity would be a constant. There's lots of different ways of expressing the connections between displacement, velocity and constant, and I'll have to stop the video there.